Our next presenter is Franco Cavadini, and he will explain his firm is called Gr3n Recycling, which is spelled trickily with a number 3 instead of a letter E. But Franco will explain his business and his need for open automation. He's kind of, I would summarize it as saying that his firm is kind of a in between a process licensor and a equipment OEM, and working very hard on new technology for recycling. So Franco Cavadini.
So good afternoon, everybody, and thank you for the opportunity of being here. So let me just talk you a bit about Gr3n or Gr3n recycling, as I tend to use. We are and what we do. The idea is just for you to have a context for what I will present later on. Well, as a company, we are quite young, and we are industrializing a process for chemical recycling of PET plastics. Our vision is the one where plastics is not to be demonized, because it's an incredible resource for human beings, but it must be seen as something that can be recovered and reused infinitely. And that can happen only the moment we introduce new ways of recycling it, which basically means chemically, decomposing it to its monomers, to its composing elements. Now, what we do as a company is that we are owner, through a patent, through multiple patents, of a unique process that is capable by the usage of microwaves to actually decompose these plastics, polyethylene terephthalate in particular, into its composing elements. And what we are going to do is that we sell our machines, so in some way our reactors, we produce them as an OEM, but we are also going to be part of the owners of plants implementing our technology. Now, let me just present you a bit the issue we are facing. It's important to better understand the requirements we have on our plants in terms of automation. Now, this is the situation of the market for PET plastics currently, where in front of almost 100 million tons per year used from virgin monomers, only a tiny amount is currently recycled by mechanical means, which means mechanically treating PET waste, mostly from packaging, and trying to reuse it mostly for bottles or downgrading it to fibers. Now, the hard truth to be understood here is that through the current means, most of what is produced yearly in the end goes either landfilled, dispersed into the environment, or if we are lucky, incinerated. Now, our technology is actually able to treat chemically even the worst of the waste, to bring those back to virgin grade quality monomers, and as such being able to close the loop on every type of products. And please, as this image suggests, consider that the problem is not really packaging, but it is fibers, it is textiles. Nobody talks about it, but actually more than 2/3 of the annual consumption of PET is for polyester. I think that half of you is probably currently wearing something made up of polyester. Now, let's get into the core of my speech. In our process of industrialization, we are currently in a step where we built, in the past few years, also across the pandemic, what we called our demo plant. And you see it represented here in a few of the pictures on the slide. It's a small-scale version of our process. By small scale, I mean that theoretically we are talking of about 500 tons of material treated per year. So it's very small compared to our full-scale industrial plant, which is aiming to about 40,000 tons per year production. Now, it's a place where we have matured our process and brought it to standard industrial grade quality. Now, when we were designing this plant, and I'm talking about 2017, 2018, our core focus, as you might imagine, was on the chemical process. But since in my past life, I was an automation engineer, I actually pushed into the, let's say, the table of discussion, the idea, since we are doing something which is R&D for the process, and we are building a plant which doesn't have all the constraints of the full industrial plant, why do we not push in a very bottom-up approach new technologies for, let's say, the automation part of this plant, challenging the usual practices of what is typical in the industry? And let me also say that the EPC contractor that actually built the plant probably understood 1/3 of what we were discussing. So what's coming out from this? Now, please consider, I haven't used the OPAF labels because I don't consider this as a pure implementation of the OPAF. But I've been following OPAF since its beginning. I've been playing with IEC-61499 since Isagraph, if anybody of you knows about it. So let's say that I knew some way by heart the technologies that are inside that. So while building the plant and focusing on chemistry, I actually pushed the usage of the technology in practice. So why is that? So why I'm pushing so much for the idea? Well, our process is modular in principles from a process and mechatronic point of view. I recognized a lot myself in the keynote presentation of this morning for polypropylene recycling, because I saw modular plants that you want to deploy, let's say, adapting their size based on the need of the plant itself. So the same principles applies to our process. So the need to be flexible, to satisfy the requirements of a feedstock, which in the end is a waste. So it is intrinsically variable. Basically, we don't know what's coming in at our gates, at the gates of our plant. So our automation needs to be able to adapt to the intrinsic variability of the feedstock in terms of the content, in terms of the percentage of PET which must be recycled, and so on and so on. I actually want to be hardware independent. I don't want to choose for our plant, and I forgot to tell that our full-scale industrial plant, the first one, is supposed to be up and running by 2025. That's time scale. I don't want it to be locked into single hardware. I want the life cycle hardware to be decoupled from the life cycle of software. So all of these brought to, well, this simplified control architecture, where I represented here the hardware part in order to then forget about it the moment I will talk about the lessons learned. A platform where we have several PLCs deployed in different parts of the plant. So some of them are in the control room, some of them are in the field, and they basically represent, I mean, the hardware topology for the control basically represents the modularity of the process, which is represented in the lightly blue box inside the slide. So what we tried to do was to recreate in the hardware, in the topology of the hardware, but most importantly, in the way the software has been developed, the functional units of the process. With the idea is that if I need to actually improve or substitute or evolve either the hardware or the software, one of them, I let the other untouched. And just to give you an idea, one of those boxes was actually built in a second moment. The TA crystallization, which means for terephthalic acid recrystallization, is actually an additional section of the plant which was built a year and a half after the other. So it wasn't even conceived at the beginning. We designed that, we integrated it, we brought it online together with the others, and we sort of, let's say, in a later stage, had a whole application for the whole plant. Now, all of this obviously, again, is possible because we are talking about a demo plant, not a full-scale one. It's not just that, because here I wanted to show, let's say, one constraint, and the one constraint was the need to use basically, especially at the beginning, only the hardware from one vendor, which was Schneider Electric. But as the plant grew, we actually used other hardware on top of the IEC-61499 standard. So we actually have an hardware-independent runtime currently running on top of multiple hardwares from different type of vendors. And with multiple hardware, I mean different type of PLCs, but also industrial PCs with soft PLCs hosting part of the code. The higher part of this picture is where, let's say, the, well, HMIs are obviously there, again, communicating with the process via 61499 protocol. But I'm more interested in that visualization server, because I deliberately hide behind that picture something which is the real running experiment of our implementation. Because that server, if I had to use another wordings, is actually an edge node. And in that edge node, at the moment, I have running an hypervisor, a virtual machine hosting a database, which is actually gathering the information from the field, another virtual machine to host different Dockers, and in particular, I have a Grafana Docker to show virtual visualization, and I also have a edge to cloud connectivity element in that Docker. Finally, there is another virtual machine which is hosting another instance of the HMI. So you might recognize, at least, again, in a very bottom-up way, some of the principles of the OPA architecture. And I'm still looking for a concrete solution to also have real-time virtual machines inside that node. Hopefully being able to host some of the hypervisors, some of the orchestrators, sorry, of the plant itself. Now, let me talk a bit about what we learned along the path, because let me be honest here, it was far away from being perfect or simple. In not a few moments, I told myself, why in the hell did I actually push to use all of these technologies on a process where the main focus was the chemistry, okay, our recycling process. But in the end, I'm happy of that because we learned a lot. Well, first of all, I think that most of the problems, most of the issues we saw are due to the fact that the current engineering life cycle for our plants is not actually well suited to be including all the principles that I've seen discussed today. Automation arrives too late into the discussion of a plant engineering. Well, too many degrees of freedom have been frozen. If we want to talk about modularity, hardware independence, designing the topology together with the process, designing the software so that it is modular as much of the unit of the process, I think that automation should go up into the life cycle for engineering. Another thing that I learned and discovered is that probably the way specifications for control are written today, which is very formalized in the process industry sector, again, is too limited to actually guide later software development according to these new principles. There is a gap between what the control engineers write in control specification and what the current software system integrators need to develop according to these new principles. Another issue we encounter is that none of the package unit suppliers that we involved have any idea of what I'm talking about. So the moment I bought, for instance, a pneumatic conveyor for our PT flakes, I got a connection via wired IOs. So how is that running up with all our principles? It is not. So to be successful and to have my full-scale industrial plant running according to the full principle, we need to push suppliers, vendors of a package unit to actually accept this technology as much as us end users. There is a huge problem, which is system integrators. So when we will have system integrators capable of dealing with these new concepts? Just for the purpose of me knowing, how many here can, let's say, consider themselves system integrators who develop actual software for plants? Okay, so you perfectly understand why I'm saying this might be a problem. When discussing with our system integrators, we actually accepted a challenge because they were using a technology which was not on the market, on a beta software, without ever having used it before, so it's quite a special one. And what result is they implemented software which was not really according to the IEC-61499 principles. So it worked, the most recent version of the plants were better, but the original version was not. Would that be acceptable for a full-scale industrial plant? No. So another problem is that there are no libraries. New technology means that we don't have an history, which means that basically we almost didn't have even a PID loop algorithm to use. Or maybe not a robust one as you would expect the moment you go and implement everything else. Another aspect is that documentation, reference guidelines are missing. The moment we talk about a new standard like IEC-61499 as it is implemented by universalautomation.org, we are talking about object orientation in software for plant control. We are talking about function blocks. There are no guidelines on how these should be written. They are coming, and obviously also the OPAF effort is gonna push in that direction. But at the moment, it's a bit too early. And another aspect which I think I found as a drawback is that the moment the control software is object-oriented, then what about the data? We found ourselves with data tags coming into a database, losing the, let's say, the semantic representation of the actual objects for control. So becoming plain data coming out from the field as in the typical SCADA way. Now, if we really want to apply data analytics and artificial intelligence, we need to gather the intrinsic information coming from the process. And this must be written together with the control objects. Otherwise, we lose something in between, which is the contextual information that data is coming from. Now, to conclude my speech, I also want to highlight what I see as our opportunities as Gr3n and our investors in going into the engineering for the first industrial plant. And just to give you an idea, we are at 1/3 of the basic engineering effort. We are already late, but that's normal in our business. So, as I told you before, modularity is essential for us from a process point of view. I want our software to be equally modular. I want it to be reusable because the moment I do the math and I see that I have an 80 million tons per year market to fill, and my plants are 40,000 tons per year, now you can do the math, you see how many plants we could eventually be, even just grasping, I don't know, 5% of the market, and you understand why I want it to be reusable. Okay, I don't want to reinvent the wheel every time one of our plants will be instanced around the world. I want to reduce the engineering costs correspondingly, which are too often underestimated. So you do all the rest, and then there is a nerd software engineering doing the things to have the plant working, and too many times you forgot how many man-hours are spent over there. And in the end, I want the TCO, the total cost of ownership of our plants, to go down, because that is going to be essential for the sustainability of our business. As Gr3n, we have patents, we have, let's say, know-how about the process, but how our machines work, how they are controlled in real time, how they are optimized in order to actually achieve the performance we want, is a huge and essential IP that found new way to be protected by this new way of writing software. Object orientation is a natural way to encapsulate software IP and to protect it in a different way with respect to, let's say, the traditional means. Well, and then there is the always mentioned aspect of data analytics. I still have to see many instances where artificial intelligence is being used in practice to give relevant improvements. In our case, I'm really hoping that we will achieve that, especially in terms of runtime optimization of our process in face of the feedstock variability that I was telling you before. And finally, our technology means a circular economy, means circularity of the supply and the value chain. It means for us horizontal and vertical integration inside that value chain, which means that OT, IT integration is essential to create value across that. Just to give you an idea, certifying that at a certain moment in time, one of our plant is decomposing plastics and producing monomers from specific feedstock coming from specific sources and producing monomers which can be deemed as, let's say, fully green by end users, by fashion brands or packaging brands. Now, it's an added value to our business. And how can I achieve that? Only by being certain that data coming from sensors can become data inside a data tag, a label, a digital label associated to a bottle or a t-shirt or whatever. So to us, OT, IT connectivity means using data to create value for our company. Well, thank you. If you have questions later on, I will be more than happy to answer you, and I hope it was not too boring as an introduction. Thank you.